And how is that so? Um, the first thing that I would like to tell you is that, see, at the beginning of the 80s, or till the 80s, you can say computers were very big entities. You could not own a personal computer. And then in the 80s, you could own a personal computer. Why? Because processing became cheap, processing became small, the processors became small, they became microprocessors, and could be enclosed within a small computing desktop computer. But that didn't start the proliferation of embedded systems. If you look into the 90s, this happened all in the 80s. We started getting, in my school, I had small, I saw desktops at the beginning of 90s. And then what happened, if you look through the 90s, memory slowly started to become cheap. In the beginning of 90s, you had very big memories. Means even MBs of memories were extremely costly, where their size were extremely big. And then slowly at the end of the 90s, you started to have pen drives, all this. So memories became miniature elements, and they were very they could be obtained with very low price. So two important things now became very low in their aspect ratios, in their dimensions, and also in their price: processing and memory. And then through the 2000s, the first decade of the 2000s, another important development came in: communication became very cheap. So you started having mobile phones, you started having the internet, and everybody could talk with each other. Data could be transmitted with almost to no cost at all. Now, so with connectivity becoming cheap, with memory becoming cheap, and with processing becoming cheap, now computers could be used within anything and everything. And we started talking about why not machine to machine talks, and we get a new system out of that. We don't interfere, but machine communicate among themselves different signals to give us different types of systems. For example, we could have systems such as, let us say, you have a wearable device on the palm of your hand or on your wrist, that can find out what is your mood. And let us say you have a light that can exchange signals with your wearable device. You have a light in your room that can exchange, and the this wearable device uh, tells your light, whenever your mood is bad, please dim the light. So then you could get an IoT, or an Internet of Things, a system out of these two things: this wearable device and this light. What is that system? That system, that computing system, that distributed computing system, talking with, which is combining both the light and the wearable device, that gives you this functionality. Depending on my mood, my light will be dimmed or my light will become bright. So this is just an example of what an embedded system is, or how embedded systems. So therefore, embedded systems are not only those devices that are within a single device, but could also be those which are enclosed or hidden within vast devices. For example, embedded systems enable us to manage vast power generation and distribution networks. Today, we talk of smart grids, where you manage the real-time demand and supply of power. So what happened in yesteryears is that you had to generate based on worst case needs, and most of the power generated was wasted because it was not used. Now your power is generated accurately, much more accurately, based on what you need in real time. So this power has been given by the power of embedded systems. Control industrial processes in the so industrial processes, assembly line processes, they have all become smart. Robotic assembly line systems, so assembly line systems going on, designing different things, so that you have a distributed cyber physical or embedded system which controls each and activity, and the parts of the car is entering from one side and the finished part is going out on the other side of the assembly line, all being controlled by an embedded system which is consisting of numerous components: computers, robots, different robotic hands, and most of these things are automated. So industrial automation is mainly, now we are looking at whatever we are talking about in industry 4, it is just due to the improvement in technology in embedded systems. So we can control automobile, ships, trains, airplanes, etc., conduct video conferencing over the internet, interactive electric commerce, etc. So all these are examples. Now, when we have given you this introduction to embedded systems, the next important thing comes: what is important in the design of embedded system? Now, why are we learning this course? Because we want to design new embedded systems. Now, so therefore, we need to understand what are the critical factors that govern the design of a new embedded system. So you have a new thing and you want to embed a computing system. Suppose you have a traditional rolling mill company and you want to make the rolling mill smarter so that the metal sheet that is coming out does not have variations in thickness in it, and that should be controlled to very precise degree through an embedded computing system. But you want to design that embedded computing system. Now what will happen? What are the things to look at? So oftentimes embedded systems have to deal with stringent constraints. For example, due to many reasons. For example, cost, size, etc. In a washing machine, you cannot use a very costly microprocessor system. In a spacecraft, you cannot include something that is very heavy. So size, weight, everything will matter. So they could be compact systems. You may need to deal with simple processors and limited memory. Why? It could be many reasons. For example, one could be that the embedded system that you are going to design is intended to be battery operated. So in that case, your processors need to be simple, your memory cannot be very high, but you need to do everything that you have to do. Okay. Um, um, it is reactive and it may require high performance. Um, it may need to be reliable or predictable. With all these constraints that are already there, it may need to be fault tolerant, secure. It may need to consume low power. I've taken the example here of a pacemaker. Suppose you want to design a new pacemaker. First thing, what is a pacemaker? A pacemaker will give you, will support you with electrical pulses in your heart whenever your heart itself cannot generate those pulses in a periodic fashion. So whenever the pacemaker sees that the heart is not being able to pump or generate those electrical pulses for pumping blood in a repetitive fashion, periodic fashion, then it will support it with the artificial pulses from the pacemaker. Now, such a system cannot have a very high delay. For example, after it finds out that your heart is not being able to pump in a very synchronized, repetitive fashion, um, it cannot take a long time before which it can respond. So it has to do its computation in quick time. Okay. And because it is embedded within the heart, it cannot take a very large area. Because it has to operate for tens or 20 years in a row, it cannot consume a lot of power. It cannot consume a lot of power from its battery. The design should be very correct. It should not fail during its operation within the heart. So the design have to be verifiable, meaning that whatever design you are doing, you have to have you have to be able to mathematically prove that all the required specifications required to the design are met. The algorithms need to be reliable. So what happens when one part fails? Suppose you are designing embedded systems for an airplane, then you have your components need to be fault tolerant. So whenever one component fails, another component will come up and take its place and try to and try to cover the fault so that the so that it is fail safe. So even the system is safe even in the presence of a failure of components. So that is called fail safe. And when you are providing numeric measures, means how fault tolerant it is, that numeric value is called reliability. Reliability is the numeric measure of fault tolerance. Okay. And then your design system has to be testable. So verifiability is on the design and testing is on the finished product. So after you have designed the finished product, you should be able to test whether during the manufacturing process. So design was correct, fine, but ultimately it was implemented on a set of processors. It made if you are in a processor, then you made a hardware device, then you implemented multiple things on the overall set of embedded systems in the place of communication, etc. So that has to be validated and tested. So that also testability should be there. And finally, resource optimization is also required because you need to make this system cheap. A pacemaker should even a person who is not very rich should be able to buy and embed this pacemaker for his patient. So therefore, these are the constraints related to the design of embedded systems. Any questions here? If no, I'll just take a no. If it is okay, we can just proceed. Because I'm talking alone, I'm not getting any feedback. Maybe just one of you can say it's okay. Am I there with others or not? Am I connected?
Yes, sir.
Yes, sir.
Okay.
Let's
Okay.
continue. Sir.
Fine. So then we come to real-time systems. Many embedded systems that we talk about are real-time systems. Now, what are real-time systems? A common notion is that real-time systems are those which must be very fast. We produce output and in no time we produce an input and in no time it produces output in response. So that is not what a real-time system is. Real-time systems it has nothing to do, many times it needs to be very fast, but it has nothing to do with how fast it operates, but rather it deals with how predictable it is. So real-time systems mean that these systems are predictable. So what do we mean by predictability? This, a system whose specification, I'm coming to the definition here in the middle of real-time systems, a system whose specification includes both functional as well as temporal notions of correctness. So what do we mean by logical correctness? That whatever you give, it produces the correct outputs. You give as input to the system, it always gives the correct outputs. That is logical or functional correctness of the system. Now there is an additional requirement for real-time systems. It needs to be temporally correct. What is temporally correct? It should produce the outputs before a deadline, before a particular instant of time called deadline. If you cannot produce the output within deadline, which is pre-specified, the deadline does not need to be very near or very far. It does not have to do with how fast it is, but the specification will include something called a parameter called deadline, and you have to always be able to satisfy it even in the worst case scenarios, that you will always meet deadlines. For example, it is not enough to say that brakes were applied. We should be able to say that brakes were applied at the right time. What is important into this is just not a non-technical statement. You can also take it as a technical statement. For example, suppose you have an anti-lock braking system. What does an anti-lock braking system do? That's also an embedded system in a car. An anti-lock braking system stops the car from sliding. That means, suppose, depending on the pressure that you put on the brake pedal, it will just release the brake and again push the brake. Mechanically, it will release, push, release, push, release, push. So that if you just mechanically, if you push the brake and don't release it, the car, because of its inertia, will slide for a long distance. Now, the anti-lock braking system, what it does is it continuously releases and pushes the brakes, the mechanical brake, so that the car does not slide and stops within a short distance. Now, technically, whatever we have placed in the slide could be told like this: the embedded systems must the anti-lock braking system must release the brake within the next 100 milliseconds to stop the car from sliding. So it got the response that it has to stop the brake. It will do some computation, and then within the next 100 milliseconds, which will be called the relative deadline, it must be able to actually mechanically apply the brake. So that's the example of a real-time system. Then we come. Yes.
sorry to interrupt. Just are you setting the stage? I mean, slide 3, because someone's asking is this.
I'm in slide 6. Are you being
So
able
I
to
mean,
see slide 6?
no,
Yeah,
that
for
is
us
a
it is
slide.
still 3.
Yeah, it's still 3. So that's it.
My God, my God.
Yes, ma'am. Same here, ma'am.
Yeah,
Okay,
yeah.
sure. But I'm going back and trying to check what is happening. I'm still sharing screen. What I could do is I could stop sharing and then start sharing again. Just a minute. Are you being able to hear my voice?
Yes, voice is fine. Just screen sharing is yeah.
Okay.
Just you stop and start it.
See, are you being able to see now? Slide number 6. Hello.
Yes, fine.
Fine. So I'm very sorry. I thought you were still here, right? So we went to this slide, and I'll share this slide as at the end of this lecture. From next class, I means whenever is my next class, I will share the slides before the start of the class. So here we were. When I talked about this pacemaker, I was here. Very sorry, I missed all this. Then I talked about this real-time system, this slide, and then finally I came to this. I'll tell the slide number. If you are not in sync with me, from now on, I'll tell you the slide number. If you're not in sync, then we will again do something. Okay. So till now, we said that embedded systems are a short form for embedded computing systems. Embedded systems could be within a single core, within a single device, or it could be distributed. We talked about the different types of embedded systems, why embedded systems became possible, and then we talked about that the different constraints related to the design of embedded systems. And then we talked about that many real-time many embedded systems are real-time. And we went on to talk about what is the meaning of real-time systems. Next, we will discuss this topic that many real-time systems or real-time embedded systems are essentially control systems. So you must have taken this in the last class, but still, so in a control system, you have a physical plant, and from a physical plant through a sensor, you take the sensor inputs and you have a reference input, and then you do a control law computation and back to an actuator. So taking a small example, so this schematic is an example of a one sensor, one actuator control system. Let us take that, think that you have a very naive cruise control system, and you want your car to continuously run at a speed of 40 kilometers per hour. So then your reference input, this RT, will be 40 kilometers per hour. And let us say currently the speed of the car, the plant is, let us say, the wheel speed. So the wheel is your plant. And then your sensor senses the wheel speed. Now this sensor, let us say, has sensed that the car is currently running at 30 kilometers per hour. And then therefore you have a reference input getting into the control law computation, so through an AD converter, and you also have this 30 kilometers per hour YK that also goes in the control law computation. Depending on the error, you will produce an output. What is that output? What should be the throttle given to the wheel by the engine so that your car will accelerate from 30 kilometers per hour to 40 kilometers per hour. This is what your control output will be. Through a DA converter, it goes to an actuator. So therefore, then again it goes to it goes to the DA converter and to the actuator and back to the plant, so that the throttle of the car can be increased. Now this happens at a constant frequency. Okay, so now I am going to slide number 7. This happens at a constant frequency. And what is happening at a constant frequency? You are continuously sensing this current speed of the car. You are comparing with you're comparing with the reference speed. You are generating the output, which should be the new throttle that should be applied to the engine, and this goes on happening at a sampling period t. Let us say every 100 milliseconds you are doing it. Now this t is a very key design choice, because it will tell you how stable your system will be, whether it will deviate too much. If the disturbance if your t is large, your disturbance could be large, and your system can deviate too much from what is the reference input. So if it is too small, the cost of the system will increase. Now this error computation that is happening in the middle, so that is this control law computation. This control law computation essentially is this code that we are showing here, this pseudo code for the control task. So what is it doing? This set timer to interrupt periodically with period t. At each timer interrupt, do analog to digital conversion, compute control output u. So you have a code running here, a software code running here, output u, and do digital to analog computation. So now what is happening here is that this code will be called this real-time task. Now you see that this controller is essentially a task. You can do this, you can implement this task in hardware or in software. That does not matter, but what you have is a task, and this task need to meet real-time specifications every 100 milliseconds, this capital T factor, and hence this is a real-time system. Now here we have two notions. Now we are saying that this is a software or a code that will run on the embedded system. So this is one definition of embedded software, and you also need software to design the embedded system. So you have two types of software involved. One is the application software that will run this control task, that will run inside the embedded system, and other is that software which will help you design the embedded system. So we will primarily deal with that software here, the softwares that are essential for the design of an embedded system. But we will also talk about how that software generates what that embedded system will be, that will run here, that will run inside this controller task. We'll also talk about that. Okay. Now let us come to what a cyber physical system is. So by the name cyber physical system, we understand that there are two components, subcomponents. One is a cyber subcomponent, the other is a physical subcomponent. The physical subcomponent is same as that of the control system physical plant or plant. So that is same. But the cyber component now has a bigger meaning. What is that meaning? The cyber component encompasses all those from the sensor to the computation and over different platforms. So here you see you have two platforms, one on the left, the small platform 1, and one on the right, platform 2. And this platform could be distributed, connected by a network fabric. So this gives me the general definition of embedded systems or cyber physical systems, that as we told in a smart grid. Smart grid, when you let us say, well, why I took the smart grid, because it is geographically vastly distributed. So there you have multiple platforms in different stations with different transformers, say, which talk among each other to find out what each one is producing, what supply it is getting, and what is the consumption from that transformer. That real-time information is being exchanged to finally tell your generation plant as to how much it should generate in the next sampling period. So therefore, when you have multiple platforms, computing platforms communicating over a network, we call that by a more generic term called cyber. And we tell that instead of an embedded system, we typically refer to that system as a cyber physical system. Now we come to how do we develop embedded systems. So we were talking about softwares required in the design of embedded systems. We will now go into that part. Okay. So think that you are to design a new embedded system and you have a hazy idea in your head. Okay. Now, what do you want to do? You have a very hazy idea. First, you need to formally and structurally represent that idea. Okay. So for that, first what you do is you decompose the functionality into manageable components. And then you model each such decomposed functionality. And what is model? Model is a representation, is an abstract representation of of the functionality that you want to design or implement. For example, a map, a geographical map is the model of an actual place. Now, map is not the place, not the physical place. Map is a representation of the place. Why is map not the place? Because it does not have the actual soil, it does not have the actual houses, it does not have many information that is not required in the physical place. That means that location. But maps hide all those information, but gives us some relevant more information. For example, what is the distance between two cities? So maps allow you to model what you need and to hide unnecessary details. So that is what you, and that is why map is a model of a physical location. Similarly, when we want to design a functionality, we first model as to what specifications we need in the model. So this should be, we say that function 1 should be computed, then this information should be given to function 2 within this much time. All these things we have to represent in the form of a model, formally represent, so that two things can happen. You can automatically generate code for it, for that model, and then from that code you can either design your system in software or in hardware. So from the code, what do I mean when I say that I can design hardware? I'll come to later, just a bit later. So in fact, next. So then is architecture selection. So in this architecture selection, when you have this model, ultimately all these models will be finite state model representations. Madam will discuss much more on this. I'll just talk about what finite state machines are in very brief. And then from such finite state, yeah, sure.
I have a query. Sir, what is the difference between IoT and CPS?
So the difference is very hazy, but you could say is that when machines communicate among themselves over an internet, they typically we typically consider it as an IoT. But the actual difference is very, very hazy. Whatever is a cyber physical system is essentially an Internet of Things. And the design procedures are almost very similar. Huh? So that's again an ornamental term that you can say. IoT is an ornamental term for a cyber physical system, which is sort of a more technical term.
Yeah, I just want to
yes.
add. Yeah, I just want to add one thing. You just check the history. Basically, the CPS one term is coined from American part, and another term is coined from European Union. And that is I mean, there is always a conflict, and they have just similar type of technology, only two different terms they have proposed. So underlying, if you go, I mean, security analysis, reliability analysis, design perspective, everything is same for these two components. Only it was proposed or almost during the similar time from two different parts of the world. Okay.
Absolutely. Maybe you can say that many modern technologies such as predictive maintenance, etc., they are getting more and more associated with IoTs. So predictive maintenance, different types of business models that are coming up. For example, auto update in an automotive system. But everything that we are talking about, it could be easily told that in terms of a cyber physical system as well. So principally and technically, there is not much difference between what a cyber physical system and IoT is. Right. So as we were talking about, if we have something in our head that we want to design, firstly that rough idea, informal idea has to be structured and represented as models. And those models will ultimately be represented as task graphs, something called task graphs, where you have different tasks and interconnection between them, also called data flow graphs or data and control flow graphs, representation, something like that. And from there you can design, you do what is called a hardware software partitioning, or in more general terms you do an architecture selection. For example, do you want to implement a certain model, a code for that model in hardware as a chip, as a custom chip, or as a software, as a C program on a general purpose processor? What are the pros and cons? If you implement it in hardware, obviously it will be very fast. Why? Because it's a customized digital circuit that is inside the chip and that is doing that specific function of that code. Okay, you have designed a combination or sequential circuit. If I go on, if I remain in the digital domain, and you have designed a processor for it. If you generate it as a software, but the point against hardware here is that if you design a hardware for one function, you cannot reconfigure it to execute another function on the same hardware. If you run it on a general purpose processor, on the other hand, your things will be slower, because you will finally represent that C code in terms of the machine code, and that machine code will run according to the microarchitecture of the general purpose processor in the ISA, the microarchitecture of the processor, and in that it will follow the steps, the functional unit. So only a few basic set of steps are there, which is defined by the instructions, and those instructions have to be used to implement that functionality. And it will be a general fetch, decode, execute kind of a execution, which will make things slower, a software code slower than its corresponding custom hardware implementation. However, in return what you get is that the system becomes much more flexible. Also, a hardware is much more costlier to design. It goes through an elaborate design process, and then it goes through elaborate design process, and the time to market is also high against if you run it as a software on an say Arduino. You generate a software and run on an Arduino. So that is much more less costly. However, suppose when do you need as a hardware? Because it's very performance efficient. Suppose you have very constrained you are very constrained with respect to deadlines, with respect to real time deadlines. Then you need to run it as a hardware. Your software will take a long time for the code to execute, and you will not be able to meet your deadline criteria. And again, if you want to design many and if you want to design many such hardware, if you need, for example, processors. So processors are not implemented on FPGAs. They are designed as ASICs. Why? Because they will be used in many pieces. Crores of them will be generated and will be used for years. So that design time and the cost will be compensated by the nature of use of that system. In the middle of a pure general purpose execution and hardware is something, there are some other things. For example, ASIPs, application specific integrated application specific instruction set processors, and FPGAs, which can execute FPGAs which give you performance closer to that of hardware, along with some more flexibility, which is close to that of software. So what you are doing here is that, given the model, depending on your requirement, you are partitioning your system into hardware and software. Which part of your entire control flow graph of your product you will design in hardware, which part will be designed in software, that you are doing. Then you are mapping the functionality into hardware and software. After that, you are developing the component hardware, and you are also developing your final programs to run on different processors. Now, after you have the different subcomponents have been designed, you have to also design the communication between them. because the entire system is not one dedicated system lying in one processor. It is divided over multiple platforms on multiple processing units. So it has to be able to correctly communicate to realize the overall system that you want to design. So hence you require the communication protocol in between. Then you require prototyping, verification, and validation as well. Prototyping means after you have implemented something, you do not design the entire packaged chip, the final product, but you design a prototype, which is a representation. For example, before designing a complete microprocessor chip, you will implement your entire functionality on an FPGA and test whether if it is working. Why? Because the ultimate design and packaging of the chip is very costly. So if there are bugs in the design, in the prototype level, if you can find it, you don't have to go to the manufacturing step. So after manufacturing comes after prototyping comes manufacturing, and before prototyping rather and after prototyping, before actual implementation and manufacturing, there is the steps of verification. So verification is the process of verification is the process of analyzing the correctness of what you have designed. So at the beginning, suppose you have modeled something. Does the model satisfy all the required specifications with respect to time under all input scenarios? How do you test? You have tools called verification tools that will allow you to test whether whatever you have designed was correct and all your specifications were correctly taken care. And validation, which goes along with the design and implementation. So which will tell whether whatever you have designed, both in software and in hardware, does it meet all the performance requirements? Suppose you have implemented your tasks on different processors on custom hardware, you have implemented the communication protocol, then you have to validate whether your system meets the end-to-end deadlines or not. We'll come a bit more on this. So to tell the previous slide a bit more in a different way, what the embedded systems design process goes through 3 typical levels. The first step is modeling, which is the process of gaining deeper understanding of a system through imitation. As I told you, maps imitate the physical location. It is not the physical location. Through imitation, they express what the system does or should do. You express what the system should do through models. Then comes design. So design is the structured creation of artifacts, both hardware and software. You create the programs, you create the hardware that you require, you schedule the software and hardware tasks among the different programs, among the different components, so that the ultimate design is realized, so that your ultimate implement system is realized. So that is what the design does. And analysis is the process of gaining a deeper understanding of how the design performs. So you have performed the design in the previous step. How the design performs or gaining an understanding of the design through dissection of the design is analysis. So it tries to specify why a system does what it does or fails to do what it should do. So these are the things that is taken care. So all these 3 phases are not independent phases. If you see the figure on the right side, these 3 phases are overlapped and iterative. So if you go from modeling and design, you find some error in the design, you go back to modeling, correct it, and come back to the design. And then if in the analysis phase, if you find some error, you may go back to the design or to the model, and back you come back. So this is the general structure. After I gave you this general picture of modeling, design, and analysis, I'll go a bit deeper into modeling.
Sir, query.
Yes, please.
Sir,
yes, please.
When we use microcontroller, microprocessor, and FPGA and CPLD,
why not? Means
no.
What you are trying to say is that microcontrollers or microprocessors are essentially general purpose processors, right? You can run a C code on it. FPGAs are a bit different. You have to do a design, a hardware design for FPGAs, and you will implement that on an FPGA, right? the image on that of that whatever you have designed, you will implement on that FPGA. Meaning, could I answer the question? So the question is this: are you asking when should you implement it on a microcontroller or microprocessor, and when on an FPGA? Is your
Yes, sir.
question
Yes.
this?
Yes, sir. Yes, sir.
Okay. Okay.
As per
So right.
the main requirements of the main system.
So when we take an example, let us say of a system, let us say an anti-lock braking system, as we just talked about. Let us say that instead of 100 it does not have, typically it is around 100 milliseconds only. You find out that you have to deal with this braking and stopping and this releasing and pushing the brakes, not at 100 millisecond interval, but 500 microsecond intervals. And you have found out that if you do so in 500 microsecond intervals, means if you have to do this computation within 500 microseconds, you can no way do it with the help of a microcontroller, because ultimately that will run as a C program based on the running x86 instructions. Finally, x86 instructions on the microcontroller. That is what is going to happen, and that will make the system slower. That same code, if you run on an FPGA, it will actually go to the configurable logic block. CLBs within the FPGA will implement that function, right? So which is essentially a digital circuit, and that digital circuit does not have your functional units. It is just a customized digital circuit for your anti-lock braking system function. It has nothing outside this. So therefore, it will be very close to a fully custom hardware. So FPGA implementation will be much faster for it. Now, in this case, therefore, you cannot implement a microcontroller based system. You have to go for an FPGA. But if you do not have such very stringent requirements on time, you could possibly many things on a microcontroller itself, because that will give you much higher flexibility. Run different programs on the same microcontroller, reconfigure your system, just update your anti-lock braking system. If it is not so stringent, just go on updating your program. Just as you update your apps, you will update your software. For example, let us say this autopilot of this Tesla car, they give regular updates over the internet, and you will not know that your car is running a new software. It will just go on updating at night, and when you start your Tesla car in the morning, you are actually having a new software autopilot, which is different from the old version. You have just updated it. So that reconfigurability is given by software implementations, but many places your designs are so critical that software implementations you cannot have. You have to have hardware. Did I answer your question?
Yes, sir.
Yeah. Okay. So we go to modeling. So now let us say, let us say you want to design a simple torchlight for an embedded system. Within that torchlight, you have to design a simple torchlight, right? So that torchlight, so what is the functionality you want to design? When it is off and you press the button, the microprocessor will send the signal to this on the light. Okay, when you press the button, and then again when you press the button, the microprocessor will ask the circuit to switch off the light. So this is the simple embedded system, and you have designed it using this simple FSM. So this FSM models the behavior of the torchlight embedded system. So here you see the first line of this slide, behavior or functional modeling. So it is the control flow among components. It shows the flow of control among the different components of your system or functionality that you have in your head. And you also design the architecture or structural model, which is the structure among your components. Suppose you will design this. Think of this as a very big functionality. This off and on, this off and light is not. These are not very simple steps. This within themselves have big programs, and you have to run one program on one processor, and the other program, the light program, on one processor, and the off program on another processor. And you have communication in between them. So model of that architecture inside, that architecture also has to be designed. What is the architecture of my platform? What is the architecture of the given computation platform that you have? So that is what is architecture or structural modeling. I am in slide number 11, by the way. I forgot in between to tell you. Are you with me, all of you? I'm very sorry. I forgot.
Yes, yes. Now,
Yes.
Okay. Yes, yes. So that's what is architectural structural modeling. And as I said, finite state machines are a very popular behavior modeling mechanism. Now, what is a finite state machine? The system moves in discrete steps from one state to another state through transitions. So you have states and you have transitions. What are states? States denote a specific valuation of system variables. Here you have only one variable. So x equals to off or x equals to on. So when x equals to 0, you are in off state. When x equals to 1, you are in another state. So therefore, you see, state is what? It denotes a specific valuation of system variables. What is a transition? It denotes a change in the valuation. So whenever x changes from 0 to 1, it goes from off to on, off to light. When you press the button, that happens. And then when you again press it, the valuation changes from 1 to 0, and you go back to the off state. Now, let us say that we wanted to design, so see that this, firstly, this design of a torchlight embedded system is not real time. There are no constraints with respect to light. However, let us say you want to design this functionality, that when you press press button, when you press the button twice quickly, you go to bright light. Okay, so when you press once, you go to light. That is a medium intensity light. If you press the button twice quickly, you go to bright light. And then there, when you again press the button, either if you are in light or in bright light, if you press the button, you go back to the off state. So what do you want? If press is issued twice quickly, then the light will get brighter. Otherwise, the light is turned off. Now, how can you include this? By empowering the finite state automata with real valued clocks, and that is called a timed automata. We will deal with this towards the end of this course. So there, what kind of modeling that allows you to do? So it says that suppose you have a real valued clock variable, and it says that at time 0, when x equals to 0, you press the clock and it goes to light. If you press the button again within 3 time units, it will go to bright light. If you do not press the button within the next 3 time units, it will go back to the off state. So with the use of this real valued clock over the basic finite state automata, you could model a real time embedded system for your torchlight. Now with this, we already talked about a real time system. I'll quickly wrap up now. We talked about a real time control system. We talked about the pseudocode which is hidden inside this control log computation. That code is shown here. And now we will look about some specific things about that code. That controller code, controller task, when executing in software as a task, when it is executing as a task, when it is executing as a program, it is called a task. Now, tasks are composed of jobs. So each time that task executes, it is called one execution of a job. Jobs have release times, jobs have deadlines, and jobs have response times for them. We will tell all these. So what you have, let us say you have a task, and that task consumes 1 unit. That blue box see the timeline below? This blue box, let us say, is the task, and it takes 1 unit of computation time to complete its execution on a given computer. On the given embedded system computer processing element that you have, it requires 1 time unit to execute. And every 5 units of time, it is spawned once, because that this is a control task. It is coming from the sensors, and from the sensor, your sample input is coming every 5 units of time. So this controller computation has to be done every 5 units of time. So therefore, every 5 units of time, you have to execute this control task, and each time it executes, it is the execution of one job, and that will take 1 unit of time on the computing system that you have. And within any time within this 5 units of time, you can execute it. For example, in the period 0 to 5, it executes on in the interval 0 to 1. In the interval 5 to 10, it executes in the interval 6 to 7, okay, or at any time in between. So if not specified, if without any other restrictions, this job can be executed at any time within each period, but it must execute with once within 0 to 5, once within 5 to 10, once within 10 to 15. So such kind of a job are called periodic tasks. A periodic task has a period and an execution requirement on the computer. So P is the period, E is the execution requirement. If you see the periodic task there within first brackets, as we told, and these jobs repeat regularly at this period P, and the execution time, it has the period P is equal to the inter-release time, okay, and it has an execution time. Obviously, the execution time cannot be more than P. If the execution time is greater than P here is 5. For example, in this example, P is 5. If your execution time is more than 5, you cannot, whatever you do, you cannot do that with using one computing system that you have at your disposal. You need to break that functionality as a parallel application on 2 processors and execute that, so that you have more computing resources, or you have to increase the frequency of that processor, but how much, that also has limit. So your E has to be always less than P. And then your utilization. Utilization tells what is the part of one processing unit that you require for this task. For example, here it says, if because E is 1 and P is 5, it says that on the embedded system processing element that I have, the utilization of my task is 1 by 5. That means 1/5 of the computing capacity of this processor must be given to me for this task, for everything, for my computing for my computing to happen within time. Okay, and from this we come to something called schedulability. So schedulability tells that is that property that tells me mathematically what is that workload given by many tasks that I can accommodate within a single processor, or within a multiple set of processors, or within a processor as well as the communication medium together. That is what is called schedulability. I will not go deeper into this. And then there are actually, I did not talk about validation. I'll just, in the next 2 slides, within the next, say, 5 minutes or so, I'll just complete what is validation here. Validation means that you want to validate whether you will always meet your performance requirements in all cases under execution. I'll take a small example. Let us say you have a control system that acquires data at the rate of n samples per second. Can we ensure that each data item will be processed in less than 1 by n seconds? For example, suppose you are doing a video processing, and you know that 30 frames per second is a very good for good video viewing, you require to process 30 frames per second. Now, which means that one video frame must be processed within 1 by 30 seconds. So can I ensure that I will always be able to process one video frame within 1 by 30 seconds? Okay. Now this kind of a constraint will come for any control system that we are designing, for any embedded system that we are designing. So to ensure that what are the problems that we want to see? Now that system that is processing that video frame, or any control system that is processing, that is doing that computation, will be implemented on something like this. Let us say you have an SoC architecture. In that SoC architecture, you have several tasks. Here, your embedded system consists of 5 tasks. Now that 5 tasks, some of these tasks, as I told you, will be executed on the general purpose processor called the CPU here. Some of them will be executed on co-processors, let us say your GPU. Some will be executed on custom hardware. For example, here subsystem A and subsystem B. And all these things must communicate over the computation platform that you have, this computation network. And when you have multiple tasks on one CPU, you must do task scheduling so that you meet the requirements of both tasks. One do not starve against the other. You must to communicate, because this is a shared communication medium and everybody is communicating, all the tasks are communicating through the same communication medium. So therefore you need to schedule the communication medium, because you have resource contention for this shared medium. You have a complex environment from which your inputs are coming. So this incoming data, if you see this arrow, you have a complex environment where different types of inputs can come, and whatever be the type of input used, in the worst case scenario, high density input, low density input, many types it can have, it should be able to process within the required time. And the intricacy of the design also could be very high. So, so your validation has to be, this timing analysis, the timing analysis, which is the timing validation, has to be performed in spite of all these intricacies. What microarchitectural intricacies? For example, you could have out of order execution processors. So they increase the average performance, but it reduces predictability. Out of order execution, speculative execution, for example. Contention among processors running on processing elements, you have to do that through scheduling. Contention for other shared resources, for example, memory, last level caches. So what will remain in cache? If you have too much workload, the last level shared cache cannot hold everything. So you will have thrashing on the cache as well. So you can have interrupts in the system. In the presence of that also, you need to you need to maintain your timing correctness. We will look at all these, how to do all this when we through this course. Lastly, ending, I'll be using many of these books. Probably will be common for both me and Ayantika. So we will be using, I will be using, at least for my side, I will be using Introduction to Embedded Systems, Embedded Systems and Software Validation, and hard real-time computing systems. These 3 are the primary and the last 2 are references. So this is all from my side for today. I will share these slides by tonight. Is that fine? So, and the last, thank you. Can I get a okay from somebody of you? Are you there with me?
Yes, we are there.
Yes,
So,
sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Fine. So I'll stop sharing now.
okay. So,
Just I'm trying to do that. Acha, Ayantika, by any chance, did you record this today?
no, it's already recording, right?
No, I did not record it today.
Yeah, it's showing your recording.
Oh, acha, stop recording. Acha, acha, yes,
Yeah,
by
yeah.
default I.
Yeah. So, okay,
How do
that's
I-
good. Actually, good.
Somebody is
So,
recording. Okay, okay. Fine, fine, yes.
okay, okay. So, okay, so uh, next, so I'm sharing my part.
Have I stopped sharing by any chance? Yeah, yeah.
So after this, on this talk, on this talk, I think there will be the most of the things will be coming for all of you. Hello, am I audible? Hello?
Yes, ma'am.
Yes, please.
Yes, sir.
Yes, sir.
Okay.
Ritika, just to interrupt you a bit, maybe
Yeah.
after half an hour or so, I will go away from this class just to prepare for that class where I am supposed to include everybody for that 5 o'clock class.
Yes,
Huh?
it's sure.
Yeah.
Yeah, we will try to because today is the first day, so we will try to, make it early. 4:45 will be fine. I'm trying to finish with it. Okay. Just so in whatever we can discuss more, what I will like to include or add some architectural concept, like someone has already asked, like a few basic questions, like when we will choose some general purpose processor, when we will choose some microcontroller, when we will choose some FPGA, and how to decide. So these are very basic concepts when we are actually designing the embedded systems. So I will try to, for this first day, I will try to give some architectural perspective, and from the next day onwards, we will go with the flow and we will start discussing about those modeling and those other typical flow of this discussion. Okay. So by now you know that an embedded system is a controller that is a dedicated function you want to achieve, and you have embedded that system within a large mechanical or electrical system. So this is the same diagram that Anukta also shared. So we can see there is some computation, some computation in it. There is some computation within this cyber physical system. Okay. So cyber physical system means one physical plant and one cyber or computing part. So this is the one example of CPS system, but we will see later that when we actually talk about CPS based system, there are few, multiple such CPS or embedded systems we embed inside for one particular application. Now let's consider here for a single embedded system, what is the characteristics? So from the previous presentation, you know that should be a single function. Like for your embedded system, whenever you are designing, that system should work for a particular single purpose. Then it should be tightly constrained. Like it should work within some resource constraints, because we will see the platforms we are going to choose, the types of processes we are going to choose, there will be some limitations. And maybe it is reactive and real-time constraints that Ananda already told in detail, that real-time constraints means whatever functionality or whatever timing requirement you are giving to the system, there must be a particular deadline and you have to finish that task within a certain deadline. So these are the typical features or characteristics when we are talking about an embedded system. So that means from the diagram or from the whatever we have discussed, now you have some basic idea that we have to design some computing processing thing, and that we need to map to some architecture. So what architecture we can choose for this computation engine, that may be a question. So what are my options? It may be a general purpose processor, it may be a single purpose processor, or it may be some application specific processors. What is the difference? See, here are the diagrams of those. Maybe you have some basic idea about those processes, but in general purpose processors, what we have huge data or program memory. In general purpose processor, we have a general ALU. ALU means arithmetic logic unit that can support a particular set of instructions through some that was defined through some instruction set architecture. So that means Here, the arithmetic logic unit or the computation, these type of general purpose processors will support. They are more general, and there is support of more program memory and data memory. Whereas if I go for this is the application specific processor. Here, everything is restricted. This ALU is custom ALU. What does it mean? It means it is made for a particular specific application or some application domain. An example is the DSP processor, where it is not that the ALU of DSP processor, it is not something that you can do any type of computation, or its hardware is not such developed. But some huge hefty operations, mathematical operations can be supported, and the underlying gates are so developed, underlying design is so developed that those are supported well in this custom ALU. So in this way, there are these custom ALUs or these custom processors. They are application specific to cater the need of particular application. Then comes the single purpose processor. Single purpose processor, if you see, there is no program memory. Here in application specific or in general purpose processor, you can see there is a block for program memory. Program memory means from where you can fetch the program instruction. But here in single purpose processor, we have data memory to store some data. We have some control logics. How the data part, data part I will come later. Let's consider how your ALU part, the arithmetic logic unit, your operating part will work. For that, we have the control logic, we have the data memory, but no program memory, because that is single purpose, and there is nothing to choose from their instruction sets. It is not that it is supporting many, more than one instructions, so that we have to store that instructions in the program memory. So there is no need of that program memory. So we can take this, maybe better understand this with example. Let's say now you have the idea that when you are designing one, let's say that cyber physical system, you have that computing part, and in that computing part, maybe you are just trying to compute. It's a very vague example. Say take it, you are just trying to compute some GCP algorithm. You are trying to run it. So what can you do? The straight way, you can write a code. Okay, this code. Now you can see this is the steps of the code 0, 1, 2, 3. The numbers are written, and these code, steps or these lines of the code, you can just think as a steps of your algorithm execution. Now, since there are some loops, so there are some, forward and backward paths. Those are basically defining that you can jump not only to the next step. These state is basically can only jump to the next state, but this state can jump to some other states also. So this is how you can arrange the states from whatever you have written in your source code. So now you know what you want to implement. This is your computing part you want to implement. You can write some C code for that, and then these C code you can break into some states. We will define formally the states, and when we will talk about FSM and all. This is just a typical example we can think when we are thinking how I have some computing requirement. My client has given that these computing requirement you have to implement. Now, how can I choose the processor? Where can I implement? How can we approach? So that is the question that I'm trying to answer. So now you have written the code, you have the state, you have these transitions that can show from which state to which state you can jump, etc. Now your next step will be to split these states to control path and data path. I don't know some, electronics background or those students, they have this idea maybe, but for some of you, maybe this is not, I don't know if it is previously done or not. So I'm just repeating in this introductory discussion. So what you can do, From these states, you have identified, see, to implement this application, I need this subtraction maybe, or some greater than, lesser than operation. So these are my mathematical operators required. Now there may be three possibilities. Like first one, I do not have any processor. I am deciding to, I have decided to develop everything from the scratch. That means I need to develop this part also by my own. So I have to develop some ALU which will support these mathematical operations that is required for this source code. Is it clear? Hello?
Yes, ma'am.
Okay.
Yes, ma'am.
So actually I'm not getting any feedback, so I don't know. Okay, anyway. So this is the mathematical operators we have to incorporate in our ALU part. That means you are designing your own custom processor and you are deciding to, you have decided to design everything. So first thing, I have chosen what I will incorporate in my ALU. Done. So these are, you can see here, these substructures, you can see this is the greater operation, somewhere not, this is the part, not equal to. This is the another operation I need to have when I will execute this case. So all these things I have incorporated in my ALU. Fine, done. Then what are my inputs? This xi, yi, these are my inputs I have given to this data path. Now next question is, it is not that all this basic blocks present within my ALU will work always. It is not that. I can see that in some state there is no, maybe if we can take this state, there is no such ALU requirement, ALU hefty operations. Again, in some state, there are some mathematical operations required. So in this case, I have to give some input to these blocks to select, to give the information when they will get enabled and when they will do the necessary computation. Like for this case, maybe I have to give signal to this substructure or to this greater lesser operator, not operating module, that you will get enabled now and you will do your computation. So for that is something we can define as our control signals. And these control signals, see, you can see here, these are the control signals. This one, the control signals. We have you can typically decide what will be the format of this control signal, and that bitwise inputs you can give to this data path so that these modules related to your ALU will get enabled and that will do some computation with respect to whatever states you are dealing with. Okay, that means in your custom processing, you have developed from the scratch everything. You have the code, you have defined the states, from that state you identified, okay, I will incorporate these modules to my ALU. Then enable that data path or enable that ALU, you have decided that these are my control bits and I will send this control bit to my data path. So this is the typical flow we follow when we do some custom design. Okay. So there may be three cases. First one we have already told, when we have nothing, we do not have processor, everything we are designing by our own. This is our custom design. We can do it. Next, this is actually I don't know whether you can see this now or not. This is for this combinational logic part, and here you are giving this your control inputs, and this is your state register that is actually storing which state actually you are working in, and based on that your combination logic is getting the input and finally it is doing its job. So this is the basic idea how you can design your own custom processor. Next, if you have some application specific processor. Okay, first discuss about the general purpose processor. This is just the reverse side of it. In this processor, what I can do, I can always split this into the states. But there, ALU part or that combinational logic part, it is already defined. You already have some general purpose ALU that is giving you the support of this adder, maybe subtractor, maybe and some extended operations. And there, what is your job? You have to just give your control instructions. That instructions will be somehow populated to that module. That actual data path related module, and that will enable those modules, and that will do your computation. So this is in case of general purpose processor. That is why if you now go back to this diagram, you see there are some program memory, not some, actually there should be some hefty program memory when we are talking about general purpose processor. Those will store those instructions that you are going to execute, and your program counter will fetch those instructions one by one, and according to that, controller will send the input to your data path, and your whatever you want, your functionalities will get executed. So these are the two opposite directions of design. In one, you have nothing related to ALU or general ALU. You are designing everything. And in another case, in general purpose case, you have this part, only you are basically soft coding or in software handling these control logic, and you are manipulating this data path. Okay. We can come in the mid. We can think about some mid processor, that is this application specific processor, where you do not have everything you want maybe in the custom ALU. For example, let's say you will be computing one e to the power x functionality. Maybe this e to the power x computation is incorporated, some instruction, direct instruction incorporated in your general purpose ALU, but not in your custom ALU. But maybe you have some multiplication modules incorporated in the ALU, and now you have to arrange your instructions. When you are writing related programs, you have to arrange your instructions in such a way that your custom ALU can, maybe not in a single instruction, but with few, after execution of few instructions, will be able to implement these functionalities. So custom, that's why for that you can understand now this instruction execution will be slow. But why your custom ALU has not incorporated this e to the power x computation? Because the application for which these application specific processor was developed, that generally does not use this e to the power x computation. This is a very specific case. Maybe we are actually taking a very specific requirement which that application specific processor may or may not support, but with some instruction modification, maybe you can try to implement that. So these are the three types of processors. Processor pathway maybe we can take when we are actually designing embedded processor. Now the question is, which one I will choose? For that, I have to understand what is the basic, advantage of these three advantages, and obviously the disadvantages of these three processes. First one is general purpose processors. I think now you better understand that this is of course when you have the support of more memory, more ALU system, more developed ALU system. This is flexibility is high. Single purpose processor, there is no flexibility. Maybe you are not going to use this for this type of embedded system development. Then application specific processor, that is one example is DSP that I have already told. Of course, if it is application selective and you are actually working in that application domain, then you can choose that processor. So now I think you can go and you can actually think whether microprocessor or microcontroller, is it a general purpose processor? If yes, then of course we have some amount of instruction set, we have some amount of memory that we can use to build our embedded computation or embedded computing system. That's why this is the basic system architecture when we are talking about one embedded system. So what we will have, of course, we will have some control unit. By now you know that control unit will actually will be there to give the control input to this arithmetic logic unit, and also some memory unit, and that will be connected that will be connected to some input and output device. Now you come back to this diagram again, where you are actually develop some develop some embedded system to support some particular computation, and this is taking input some other sensors and doing some computation and sending that output to some other computing device. Maybe that is another embedded system, or some plant directly, some other sensors directly. So many, based on your how you have arranged them, this multiple embedded system, many options can happen. Just to include that, maybe you know what is the difference of von Neumann and Hubbard model. In von Neumann, instruction memory and data memory are clubbed together, but in Hubbard model, they are separate. In modern modern processors like ARM, those we generally use in embedded system scenario, there we generally, they have generally used modified Hubbard architecture, where some part of this data and instruction memory they are shared. Now, what is the reason behind this? What are the advantages and disadvantages we can consider when we are choosing this type of models or considering some models? See, when we are keeping this instruction memory and data memory separate, there are huge effects in terms of designing safety critical or secure embedded system design, because there are, we have another course. I'm not going to take much time here to discuss this. We have another course about security awareness, CPS and IoT design, where we see different attacks, where these attacks on your embedded system is only possible because instruction memory and data memory both are merged. The thing is that when we thought of designing CPS before, that time CPS was developed for isolated applications. That time we have not thought that it will get connected to IoT, it will get connected to internet or intranet, and it will give some more applications. So that time these type of security reliability issues that was not taken care, and at that time when embedded system architectures were considered, that time maybe people have considered these type of architectures. But now most of the systems, ARM and others, they consider this Hubbard model, where they keep this instruction memory and data memory separate. So now we have got the basic understanding what we have in our embedded system architecture. Then the important thing is that why we are considering this course as embedded software design. We are not talking much about, why we have not named it embedded system design. The answer is that when I am not a general processor designer, I am just one embedded system designer or embedded processor designer. At that time, I generally use the this first general purpose processor domain. I mostly work in general purpose processor designing domain. So here, what I have already, I have this general ALU. So I am not thinking about the total architecture. I am just focusing on the control logic, and I am just, I'm just programming the memory and control part, and my job is done. That's why most in this domain, most of, general, these type of implementations are considered as a software design, because software means what? You are handling with some data, you are handling with some instructions, and you are instructing to some system that what to be done. That's why when we are talking about embedded controller design or embedded system design, we must detail we are focusing on embedded software design, because we are ourselves not focusing on the entire architecture part. We are just focusing on the controller and memory programming part to get with some instruction sets to get our job done. So now we have understood maybe with some bits and pieces that I have some software requirement, computing requirement that I have to realize in my embedded system. Fine. So for that, with this different pros and cons of general purpose, maybe sometimes I can choose application specific processors also. And I have chosen a platform on a processor, on which with those architectural details, I have realized my computing design. Next, what I have to do, of course, I have my processor now. Now I have to realize that processor implemented in some IC. Now that part I think is quite clear to, especially to the electronics engineers, that IC, that is mainly the bottom layer of ICs consists of transistors, and then based on those transistors we form some logic gates and some connected wires on top of it. Based on these, what type of ICs you can choose, there are two types mainly. One is full custom and another is semi-custom, where in full custom you can optimize all the layers. Okay, and in semi-custom we mostly work in this because there are different advantages of working in the semi-custom design, where we have these transistors and gate levels already built. Just we do some programming on top of this wiring layer, where we do some connections between these gates, or we remove some connections between these gates or basic blocks. So maybe someone was asking when to use that microcontroller, when to use a FPGA. So that is another question. We come into that. But before that, this is the PLA and FPGA part, where when we have talked about this semi-custom ASIC, these are the two examples of PLA. These are the two examples of that semi-custom IC. One is PLA. You can see here, basically PLA means programmable logic array, where you have few logic gates, array of logic gates. But FPGA is not so simple. It is a bit complex, but it has its own advantages. You can see that the same thing another was also telling. FPGA consists of some configurable logic blocks. Now, these configurable logic block means you have some that is consists of some LUT lookup tables and some flip-flops. So, whatever specification we want to implement in that domain, maybe in FPGA, we have to realize that in terms of these LUTs and these flip-flops, basically we have to understand those specifications in terms of these configurable logic blocks. Basically, we can map those specifications to these LUTs, and we can realize the outputs of FPGA, and that is the basic technology how we are realizing our design to our FPGA platform. So these are few steps we can take, starting from our specification to our processor choice to realizing that to our IC or FPGA platform. Now, one thing we have to be clear, that choice of IC is independent of processor strengths. That means you can choose any types of processors. You can choose a general purpose processor, and you can choose application specific, and choose it to implement in different types of these basic platforms. There are some pros and cons of that. We are not going to the detail of it. But one thing we want to explain that since our IC technologies and everything is improving day by day, so whenever we are actually incorporating one IC for one particular application, in that IC, nowadays it is not that I can only do general processor programming, soft programming. I can also use some part of the IC to do some hardware programming. That means in the same IC, I can use some part for the CPU programming. I can do some part. I can use some FPGA block present in that IC to do some hardware programming. So, what is the advantage? Advantage is that is actually already told in the previous presentation, that when I have certain specifications, this is the system specification, I can divide my specification into some hardware specification and software specification. And I can take one hardware part and software part in parallel, and then I can do the final integration to get my design done. What is the advantage? Of course, you can see here in this example, like here in this case, one part, this is the processor 1 and processor 2, and this is the hardware. That means I can take the benefit of both. Processor 1, processor 2, those are actually handling my soft implementation, and this hardware is giving me parallel. Mostly we move our design to hardware when we want to go for parallel, because of course parallel implementation is promised to give me some better performance. On the other hand, when I'm going through some software implementation, it will give me advantage of sequential implementation. Now, why I'm telling the sequential implementation is advantageous? It is often simpler to implement. It is not that there are different multiple steps required to realize that parallelism in hardware. That during our course, when we will discuss on the hardware software co-design, that will be explained to you. But the main advantage is that when we want parallelism, or when we see that okay, my design will make, see here for this design, some threshold, some timing requirement is given. If we see okay, with this software implementation, with this platform, this timing requirement is getting satisfied, this delay requirement maybe is getting satisfied, then it is fine for me. I can go with the sequential implementation, and I will not take much the headache of this hardware implementation. But if not, then I have to at least explore some paths that will support parallelism, and hardware platforms like FPGA platforms, they are better for this. So for this reason, it is important to analyze our specification initially and to check whether whatever processor, whatever platform we are considering, that will satisfy all my constraints, my delay constraints, my resource constraints, and if there is anything else. So based on this, we have considered the embedded system design model. So this is a typical V model. What is V model? What is the pros and cons of it? Everything will be discussed when we will come to the software engineering part of our course, maybe Professor Sharkar will take. But what is important to understand here, what are the steps we are basically taking? For this design flow, first we have some requirement analysis. We have some requirement models, maybe some client or someone has given to you. For that, your objective to come to this part, to do this implementation, and then implementation should satisfy all the constraints. Now, for that, you have to do, maybe if it is software implementation, you have seen that, you have analyzed that it will work only with the software implementation that is good enough. Other than that, if not, then you are going for this hardware software co-design. Once that design is done, you are moving for this test implementation. I mean testing. Then gradually these are different terms of testing: module testing, system acceptance, everything. So I'm not going to the meaning of those separately now. Later on, we will come back and again we will discuss in detail way. But just want to say that due to this design model, you can see I have my specification initially given by my client. Now I have designed, I have implemented, I have taken all this effort to going through this path. But when you have reached at the system acceptance stage, you have seen maybe client is asking in between, maybe not at this stage, maybe in between somewhere, that your embedded system should work in some other environments also. Or during the system acceptance stage, you see that it is not working due to some other peripherals or some other environment related reasons maybe. So it will be very costly to again go back to these stages and to start from this stage, and then again come to this hardware software co-design, then go for the testing phase, go through this testing steps again. So it will be very costly because most of your efforts will be wasted. So that's why in this design model, we will be considering and we will be giving importance to this modeling of the system very much, where we will analyze the system, analyze the requirements, whether it is as per that whatever processes we are considering, what are the other components, peripheral components we are considering, what are the networking requirements we are considering, whether our model is as per the requirements or not. Basically, this modeling you can add already. Of course, I will not go into the presentation on the hard store. This is basically the prototyping of your design to check, to analyze deeper whether it is fine to go for this implementation stage, because implementation stage is quite costly compared to this modeling, because there are different modeling tools, software tools. You can go use that, you can do the modeling, and then when you are okay with everything, then you can go to the actual implementation. So basically, we will next day we will start with this modeling different techniques, what we will be incorporating in our embedded control design process, embedded software design process. We will take this in detail. So here are a few terms. So one, testing, maybe when that you can go by your own. Testing means when you are giving input and you are checking whether the actual system behaves as expected or not. Simulation refers to a running system for a given input, but these are not all, because maybe you have generated a few test inputs and you have tested your system based on that. It may happen that some critical test inputs was not considered in your test list, whatever list you have considered. So that means maybe because embedded system is very, there are different dimensions of it. It is having interfacing dimension, it is having delay or resource constraint requirement satisfaction dimensions. So there are different dimensions. It may happen one or two test inputs you may have missed, and maybe that was, that came when it is your design is actually going to the system acceptance phase. So you are here, and at that time, due to some test input from the client or some outsider, it is getting detected that you have missed to check some part, some functionality, some requirement related to the system. So, and also exhaustive testing is very it's actually infeasible. It's not always, you cannot promise that you have done exhaustively or you have considered all exhaustive testing. So that's why that we will discuss in this course the technique taken here is formal verification, where again there will be some modeling techniques, and on that model there are different operators that will be related to formal verification, and there, based on those operators, we will formally verify that whether our system is fine or as per requirement or not. So all these few steps we will be so why modeling is important we have already discussed. Maybe I'm not going to the slide. This is an explanation of that model. So all this, whatever I have mentioned, these will be discussed in our flow of discussion in this course. So this is the flow of our discussion where we will, today was the introductory class. Then we will be starting with this modeling part and then the design part. And here in the design part, when we will discuss, we will see, in spite of the fact we are considering embedded software, that for this software design, I don't need any architectural actually knowledge, but actually that is not the proper idea. To be a good embedded, to design a proper, or to design a good embedded software, of course, the designer should have some specific critical features of the architecture. I mean, the external architecture. So how those parts are actually affected, like memory part, in that memory part, like how the cache, how the existence of interrupt, how the other pipeline strategies, how they are actually affecting the embedded software design. So those parts we will take care of when we will actually go to this design part. But initially we will start with this modeling part, and then Professor Shorter will be taking for this scheduling, real-time scheduling, those parts. Okay. So this will be the tentative flow of our course. And also another part we will be discussing, that is the embedded communication. Now, by the name you can understand that embedded communication means how two embedded systems can communicate. It defines how the data or common exchange can take place between two embedded systems. Now, initially you understand that by communication itself, it is having just one purpose, that it should communicate some signal, some data, or some voice to the sender, to the receiver. But when it is coming to the embedded scenario, you are having different types of systems. You have having different types of requirements, different bandwidth requirements, and also you are having some delay constraints. So how to cope up with that? Just this is one example of today's smart card. We will take these examples again and again. Like you can see, this is one smart card. This is one example where huge numbers of embedded systems are heavily used. Okay. But when you are communicating, you can see when you are communicating between this engine control, or you are communicating or you are defining some communication protocol for the whole backbone of the car, those are not same, because there are some intrinsic requirement of those specific ECUs, or at this stage we can say specific modules, specific bandwidth requirements, specific delay constraints, specific other constraints. We cannot at all use same communication protocol in every part of these cards. For these cards, you can see there are different types of protocols already named here: CAN, FlexWay, MOST, and for the whole backbone, Ethernet. So these are the different protocols only we have to consider for just to develop one single embedded cyber physical related application. Now you consider these diagrams. This is the card you have developed. Now just think when this card is moving to IoT framework. So someone is asking what is the difference between the cyber physical system and IoT. You can think when this card is isolated, this is only some cyber part some computing.
Excuse me, ma'am. Sorry to
Yeah.
interrupt.
Yes.
Yeah, like we have a class from 5 to 6.
Okay, no problem. We can
Yeah.
take it. Yeah. Okay. So these are the actually I wanted to just one slide I want to show you that this is the flow of the course we are going to tell, and these are the tentative topics covered. Now I hope you can understand why we have incorporated these topics in this course. And here I have given this is the books and slides. This is a drive link you can access, and there you will find a few books. I mean PDF of the books already there. And as and when required, we will again upload some papers and presentations. And here is the reference you reference from for this slide. So that's all. Okay. So you can go for the class. Maybe next day we will start with the modeling. Okay. And if you have any questions, maybe we can take next day if you want. Okay. Yeah.
Ma'am, my problem is that I have timetable slot clash. So
Okay.
I kindly request you if you can share your and sir's timetable so that I can discuss it with the other members who have registered for the course, and if there is any possibility if you can change the slot.
Okay, fine. I will. We will actually mail you this our slot. Is that fine?
Yes, ma'am. Okay, ma'am. Sure.
Okay. Okay. Fine.
Thank you so much, ma'am.
Okay. Thank you. And whatever questions you have, we will take it next day. Okay.
Okay, ma'am.
Okay. Fine.
Thank you.
Thank you. Okay. So that's all for today. Hello. Yeah.
Can we get the slide?
Yeah. We will share the slides and we will try to share this. This one also. Someone has recorded, right? Right. I will check whether I can see in my dashboard. If not, so if whoever is recorded, can you share the video of this audio of this course? Someone is recording. Maybe I will check who is recording. Okay.
Yes, ma'am. Yes, ma'am.
Okay. Please share. Okay. So we will share the slides. Okay. Fine. Thank you. Thanks for today and.